All right. I want to start by giving a concrete example of Newtonian mechanics or ballistics, or however you want to call it. So this is what you need if you try and estimate the trajectory, let's say, of the satellite that you're trying to shoot up. So example, Newtonian mechanics. We need to define our hidden state. And I will here assume that we live in a 2D world, not in a 3D world, just to save me from writing so many components. And I'm going to say that for sure we will be interested in the location of our object of interest. So its x location and its y location. And then the velocity it has in x direction, the velocity is in y direction, and the acceleration in x and the acceleration in y. That's the hidden state. And our state evolution equation dictates that the next hidden state equals a times the previous hidden state. So we can now reason about what this matrix A should look like. Well, and the new position is going to be the old position plus time lag times our velocity. So I'm putting 1, 0, delta t. So my new position is the old position, or the old x position, plus delta t times the velocity in x direction, plus 1/2 over delta t squared, the acceleration in x direction, and the y does not matter here. Then we have something similar for the y position. And for the velocity itself, the new velocity is going to be the old velocity plus delta t times the acceleration in that direction. And we assume that the system has constant acceleration. So that would be the matrix A, which, when I apply it to the previous hidden state, extrapolates or gives me a prediction for my new hidden state. And yeah, with that, we can now look at the inference itself. So here I wanted to add, here we know what A looks like. Sometimes, let's say, if we study a biological problem, we want to track the parameters of some cell over time, then, and by parameters I mean the internal cell state, let's say, what's the biochemical state of the cell over time, then we won't know what this matrix will look like, or we may have a hypothesis, but we will need to estimate it. But here we know Newtonian mechanics, so we know what this state evolution equation is going to look like. All right, now for inference, we are interested in the probability of ZT given all observations from 1 up to t. And the equations that we will write now are the same ones as we had for the hidden Markov model. Except with the hidden Markov model, I argued that let's use the joint and ignore the denominator. Today I'm really writing the conditional distribution here. But other than that, it's really the very same thing. So this one, I can obtain it by marginalizing out z. So I can write here the joint distribution of zt minus 1 and zt, still given all these observations. And I can marginalize out this second variable. So here, in fact, I could write equality, because that's exact. And now this joint distribution of zt minus 1 and zt and x1 through t, I'm now interested in singling out the observation xt. So I can write this is xt given all of the rest, zt minus 1, zt, and x1 through t minus 1. So what I've used here is that the probability of A and B given C and D I can always write this as the probability of D given A, B, and C times the probability of A and B given C. So that's what I've used here. All right. Now, we know by looking at the state space model that in fact xt is conditionally independent of these terms given zt. So I can simply write probability of xt given zt, and that no longer depends on zt minus 1, which is why I pull it out of the integral. And then inside the integral, we can separate here the probability of zt given zt minus 1 and the observations up to t minus 1. So here I've used just the fact that I can express a joint as a... So I could say that what I had here was the probability of A and B, and what I had down there was the probability of A given B times probability of B. And there was plenty of conditioning involved, which I've omitted here. Okay. Sorry, it was too fast. So it's really the same thing as last time. And now we can again look at the state space model and see that zt given zt minus 1 is conditionally independent of this. And hence obtain this final expression here. Probability of zt given zt minus 1 times probability of zt minus 1 given x up to t minus 1. And if we looked where we started, and if we call this here alpha t, then what we have here is alpha t minus 1. And we have a recursive expression. Okay. So the way we specify the Kalman filter, we said that the very first hidden state actually is a normal distribution. We said that our state evolution transforms this linearly and adds Gaussian noise, so this is still a normal distribution. And then we marginalize over one variable. And if we marginalize some variables out of a normal distribution, we get something that still is a normal distribution, and we multiply it with a measurement term that's also normal distribution, and hence we know that this thing here, whatever it is, will also be a normal distribution. So we're looking at the probability of zt given x 1 through t. So we can infer that zt given x 1 through t also follows a normal distribution. And I'm just going to give it some dummy names to the parameters. Let's say this is a normal distribution centered at mu t and with a covariance of Vt. So what we want to get out ultimately are this mu and the V. Now actually, let's say, assuming that we had already solved this part of the problem, then this normal distribution here, what it describes is the distribution of zt given all previous measurements. And I'm going to call its parameters mt and pt here, and these are also unknown. So let's say I'm putting here in red all of the things which are unknown at this point. And we know the parameters here of this x t given z t. It's normally distributed around z with a covariance of sigma. How do we know? Because we can look at this. I'm scrolling back up and looking at this. So Vt has a zero mean. That means given Ct, my observation X will be located here at Z times Z with covariance of sigma. Okay. Now that's horribly many parameters. Did you understand what he said? And I want to first look at these equations in broad terms now. So this thing here is after I've started running my variable elimination across some previous time steps. I can argue that this is my prior. It's what I currently believe my hidden state to be, given the previous measurements. So this is the prior for ZT, given x1 given past observations. And this here is the likelihood of our observation X. So we have this prior, we have this likelihood, and now we can remember, rewind by 1 hour and scroll way up. And that's exactly what we were looking at up there. Yeah, we had a prior and we had a likelihood. We even used similar letters. Okay? And we're interested in we had a prior, we had a likelihood, we're interested in the posterior. And you see now why I introduced here this linear transformation capital C, because we need it now. All right. So we had this result, and that means we know how to combine. Namely, we will add up the precisions, and we will take a weighted combination of my prior, mean, and my new observation. Okay, so we will, for the moment, pretend that MT and PT are known, and afterwards figure out what to do about them. Okay, so for now, I pretend that this here is known. Then in that case, we can use the equations from further up, given results from earlier today. We can say that this Vt is the sum of the precision matrices. And mu t is this weighted combination. So this here, this MT, was our predicted hidden state mean. And this was the new observation. And then our posterior is again a weighted combination of the two, weighted by the relative precision. So that is precisely what we had earlier today, and is the reason why we derived that result earlier today. So if only we knew this MT and PT, we would know how to obtain our new estimate. Now to relax a little bit, I'll draw a picture, and then we'll talk about finding MT and PT. Let's start with a picture where I'm trying to draw simultaneously. This is some space, and I'm trying to indicate here the uncertainty of the position by drawing a Gaussian, by drawing an ellipsoid. And I should also indicate somehow the estimate of the velocity, let's say. So I'm using here blue for location, and I'm using green for velocity. So let's say the system here is thinks that it's moving right with maybe an isotropic uncertainty in the velocity. Now, if I make no new observation, then I am simply asking, what do I expect my new hidden state to look like given what it was previously? And we've seen this matrix A, so we said that the new location is going to be the old location plus velocity times time lag. So let's say I'm now interested here for delta t equals 2, so I'm not getting too much overlap. What is its uncertainty in the location going to be? And it will be, let's say, something like that. And I also need a new uncertainty for my velocity, and let's say it looks like that. So again, these are single equicontours of a Gaussian. Now, why did the uncertainty in the velocity become bigger? I'm going back to the definition of the Kalman filter here. Because we had this innovation noise. And I have some innovation noise on the location, but also on the velocity. So that means without making any observations, as long as I introduce this innovation noise, I get more and more uncertainty added to my hidden state. And moreover, for the location, I have an extra contribution. Namely, I had an uncertain location. Let's look at what A looked like. My new location is going to be the old location, which was uncertain, but I also multiply with the velocity. And I also had some uncertainty in the velocity. So this exacerbates, it increases the uncertainty I would have anyways. All right, so this is why after 2 time steps, I have even more uncertainty both in the location and also in the velocities. Let's say I'm waiting a further 2 time steps. And I'm getting a larger uncertainty still. Okay, so we generally expect our object to move right, but we're less and less sure where it is, and we're less and less sure how fast it's actually moving. Now maybe that's a good point to introduce an observation. So let's say we have now made an observation, maybe here. This is my measurement. At time here t equals 4. I'm only showing the measurement. Let's say the measurement only measures location. So this is the measurement of location at time t equals 4. And now you also see why this projection operator was important, because I have that this measurement x4 equals c times z4 plus again this noise. What letter did I use for the noise? It was a v. And in this example here, I'm using as a state space location and velocity. So this vector z here is 4-dimensional, but my measurement of location is only 2-dimensional. And this operator c here is a projection from 4D space to 2D space. All right. So we have our new measurement here, and now we need to compute the posterior. So the blue thing here was my prior, the red thing was my likelihood. So I can again draw in purple what is the posterior. Well, and given that the likelihood here has a so much higher precision than my prior, it will very strongly dominate the measurement. Yeah? So perhaps my posterior, okay, that maybe was exaggerated a little bit, but it's perhaps around here. That would be my posterior. So the posterior here would be, this would be Z4 given all observations I have to date. I'm writing x1 through 4, even though here in practice I only had a single observation so far. Good. This was my new posterior. And now we need to, I've only shown the posterior here for the location, but not for the velocity. My new estimate for the velocity would perhaps be, I'm not quite sure which color to use. I'm using green. So that the object only moves to the right was clearly wrong. So I need to update my velocity estimate and say, well, maybe it showed a little bit to the bottom right corner. But actually here I still have a, well, and I can also estimate, given that I started somewhere here, and given that after 4 time steps I'm there, this also gives me some information on how fast have I been. So I've learned something about my velocity also, and the uncertainty has become, of the velocity has become much smaller. All right, and given this information, I can now maybe wait another 2 time steps, let's say delta t equals 2, and get a new prediction for where do I think I will be after another 2 time steps. And maybe I will then say that after another 2 time steps, I think that my location could be somewhere around here. You see that this location uncertainty has again grown thanks to this noise term which we had here, yeah, thanks to the innovation noise that keeps increasing the uncertainty in my hidden state as long as I don't make observations. All right, so I've been here telling a story in pictures, and so the important thing is in terms of location, yeah? We started here, our uncertainty grew over time, we made a measurement, we then, at this moment, we're pretty sure where we were, not quite so sure where we were moving. We made our next prediction here, and we can make another prediction, maybe after another 2 time steps. Maybe I think I will be somewhere here, and hopefully I will soon get a new observation, and that will tell me how to update my hidden state, etc., etc. You had a question?
Yes. Why is the dimension of set 4?
Why do I mention Z4? Just because, you know, this was, I said this is 2 time steps, and this is 2 time steps.
Yeah.
Should I call it Z5? Okay.
If you would have asked me what is the dimension of set, I would have said 6 because you have 2.
Oh, excuse me. What is the dimension you asked?
Yeah.
Okay. All right. Sorry. In the here the dimension is 6. You're correct. And in my story the dimension was 4 because I did not talk about acceleration. Okay. Good. Now, there was a long story, and you know everything hand drawn. Let's look at a more quantitative picture. I should copy it with the source, which is not given. I'm sorry. This was from the. This one is from the Barber book. So this was an example, if not to say story. Here's another example. From the Barber book. What we have here are spatial locations. We have a 2D space. We had some true locations that are here shown in red. We had observations, which are here shown in green, over time. And we have blue, that's the result of the Kalman filter. So it's the best estimate of the true locations, which, however, are hidden. What's not shown in the picture, unfortunately, is you know, the certainty how it develops over time, and you know, just to stress that this is not the same as nonlinear regression or so. This could, of course, you know, go on depending on whatever observations we make. This can have, you know, give all kinds of trajectories. All right. Do you have a question for the story? Yes.
In the example of the Barber book, the measurement noise is very high, is that correct?
Yes.
The
measurement noise, as you see here, is extremely high because the true locations are given by the red crosses and the observations are the green ones, and you see they're quite far. So there's a lot of measurement noise here. Yes?
Can my model forget? Because maybe at some point it doesn't make sense. I don't know, like maybe it doesn't make sense to remember where I made my first measurement.
Yes, the model does forget over time. And well, how quickly it forgets depends on the precisions of the measurements that you make. So if I pretend that my measurement is highly precise, as I've also tried to indicate here, then yeah, the model will be willing to forget whatever it thought before.
But it's forgetting in the sense that the coefficients get small, or is it forgetting in the sense that it will consider something that happened in the past? Was it clear?
Your question is clear. I think the best way to what's the best way to answer? So by forgetting, you mean change its opinion drastically with regard to what it was earlier on? Or?
Yeah, more like maybe at some point it doesn't matter anymore, like where I was in the past.
Yes.
Maybe if I had a trajectory, maybe it's totally independent after 2 minutes.
Yeah, there will be some kind of, if all the there will be some kind of exponential forgetting, I think, because we always have a combination of the deterministic part and the innovation noise, and over time this innovation noise can drown whatever happened before, but I'm not sure if it's actually exponential or what it is. So I cannot give a very satisfactory answer, I'm sorry. Maybe a question that I can answer? Yes?
Like, how does the noise influence the results? So noise are like hash parameters you have to choose, but how does it change the outcome?
Okay, so you see that we have many parameters. Yeah, how big is my measurement noise? How big is my innovation noise? Let's say if I make the innovation noise large and the measurement noise small, then my system will always believe the measurements and the hidden state will update very quickly. So in this example here, if I make my measurement noise too small and my innovation noise too large, then we don't see the temporal ordering of these observations here. But then I would update the hidden state according to the way these observations come in. Yeah? So I overfit the data. If, on the other hand, I make the measurement noise very large and the innovation noise very small, then if the thing initially thought it was flying in that direction, then it will go on believing that no matter what you measured. Yeah? So qualitatively, these are the two extremes. And then, the art is to estimate the parameters well, to get not too much bias on the one hand, but not too much variance or overfitting on the other. More questions? All right, we have a few minutes left, and we need them because we knew what to do once we have this normal distribution and once we have the normal distribution after marginalizing out this variable. So this was when I said for now I pretend that MT and PT are known. But in practice they are not, and we need to find them. And this equation here, this update equation, is also known as Chapman-Kolmogorov equation. And let's look at that equation again. We have, on the one hand, a mechanism that propagates my past estimate of the state into the future. And we have, on the other hand, our best guess of what the past state actually was. Yeah? And I now switch to the, or you have this in the public document. This is chapter 233 from Bishop. And by the way, today when I used the Kalman filter, so the letters that I used were also the choice of Bishop. And if you haven't looked at the book yet, it's a really good one. And, on the homepage of Bishop, you also find a PDF of the complete book. And we're looking here at chapter 233. So what we are interested in here is we have y equals ax and a plus b, which I don't care about, and we have some random variable x. So in our Kalman example, x would be z t minus 1 given x1 through t minus 1, and the y would be zt given zt minus 1. Okay? And this chapter talks about how to first find this joint distribution of x and y, and how to then marginalize out x. So it looks at the integral of p of y given x, p of x dx. And I could write the same thing on the right-hand side. This is our Kolmogorov-Chapman equation, okay? T minus 1 given zt. Oh, the other way around. Zt given zt minus 1 times the probability of zt minus 1 given x up to the last time step. Okay, so this is how you can translate what's written in this chapter into what we need. And Bishop shows you how to proceed in several steps. First, we do the very same thing that we did at the beginning of today, namely comparing coefficients. So you first write down all the second order terms, and you define this joint distribution of x and y. You then find its precision matrix R, and by comparing all the second order terms, you find that this precision matrix is this. But we don't need the precision, we need the covariance. And to go from here to there, you invoke the matrix inversion lemma. A few terms cancel very nicely, and you find this covariance matrix. Then, after looking at the second order terms, you look at the first order terms to get the posterior mean. And the posterior mean is this. Yeah? So what we have here is the posterior covariance. What we have here is the posterior mean. And if we now want to integrate out one variable, I'm not calling it posterior because it's really the joint distribution. Let me write joint covariance and joint mean. And if we now want to integrate out one variable, if we only care about the distribution of y and not about the distribution of x, then we can simply, from this covariance matrix, omit the terms that we are not interested in. So we can simply take from the mean the second part, and we can take from the covariance matrix this bottom part. And this is what you see here. All right, and now if you replace all the letters used in this chapter with the letters that we have in our derivation of the Kalman filter, then you finally get to this result here. I will copy it in the public document. You get this result. Namely, it says the covariance of my new hidden state estimate, given only the past observations, is my old uncertainty projected into the present with the model noise added. That's what we see here. And well, the expectation is just the propagation forward of the previous estimated mean of my hidden variable. Okay? And now we were having in this equation, we had the unknown PT and the unknown MT, but now we know what they look like. Yeah? So with the equations on this page, we now have everything we need to run the Kalman filter, to run this recursive inference scheme. Final remark, in the literature on Kalman filter, if you look at, let's say, the Wikipedia page or something on the Kalman filter, you always find a formula that uses the so-called Kalman gain, which looks slightly different from the formula that we have here. The result is the identical one, but you need to invoke the matrix inversion lemma once more to get from the form that we have to the form that's frequently used in the literature. But the result is the very same. As literature for today, I recommend Bishop. I recommend the corresponding chapter in Murphy. And there is also another book by Simo Zerke, which is also available online. So literature, Bishop, or a book by Zerke, which is called Bayesian Filtering and Smoothing. Good. Thank you. Thanks for sticking with me, and see you on Wednesday for Anna Kreshok's talk. Thanks.